Today's topic is a collection of other evidence. With the other evidence, I usually mean stuff that is not on the systems where we have already acquired memory or hard disks from. So this will mostly include log messages first from the compromised systems, forwarded to some central log host or seam or whatever you have in this place. But it's also log messages from other systems that may have logged activity that belongs to the incident we are trying to investigate. So this may include firewall logs, routers, switches, especially the association of MAC addresses with the IP addresses, NAT gateways, VPN gateways, wireless LAN access points, and lots of other servers like DNS servers that may have included a dynamic name to IP address mapping or included some service records that were dynamically allocated. Think of Active Directory here. DHCP I've mentioned, LDAP servers, which is always useful, especially when you see lookups to keys or some other stuffs in the corporate directories. LDAP is also what's behind Active Directory. CIFS or NFS servers or even AFS or whatever you have as network file systems where probably accesses have been logged or mounts have been logged. The activity of your backup servers. Attackers sometimes try to disable backups, so there may be something in the logs here. Key distribution centers from Kerberos, again, think of Active Directory domain controllers. And then there's, of course, all the virtual machine hosts where you might have hosted your compromised virtual system. They all may have something that we might be interested in. The other big part is network traffic data, but this is the part where Toby will come in. This is mostly about packet captures and flow data. And there's some more data. This is not entirely technically, not entirely something that can be easily put hands on, but it's still quite important, like the hardware configuration or some information about the users and the role of the system that we are investigating. So let's start with logging. So in general, whatever type of log system we have, and all operating systems have some sort of log facility built in, a log is just a sequence of entries generated by the operating system or the application telling about its activities. The key points are here. What is being logged is usually not determined by the system administrators or the users, but by the programmers of the application or the operating systems. And as admins, we can only filter these down to a subset or enable a larger subset to be logged. The usefulness of log messages varies greatly. So be prepared that about 99% of it are irrelevant, but the last remaining 1% is usually indispensable for our investigation. So the art here is just to filter out the useless parts. And typically the logs are stored on the system that generates them. So when we make a hard disk images, we will already have collected the log files and usually also the deleted log files when we do a image of the partition with the log files in. So, as a point to remember when we do imaging of systems, see that we have the partition that contains the system log files with it. Sometimes it's on separate partitions, but mostly it's on the same partition as the operating system itself. So it's C on Windows or root on Unixoid systems. And of course, when we think about logs, they may also be forwarded to a central log host. So, and for comparison, we might want to get a copy or a subset of them without making a disk image of the whole log host. So, but there's also a problem from the forensic point of view. Once a system is compromised, the adversary can completely delete entries or the whole log file, or they may change the entries or even generate false entries. They may also do this for events in the past. So, and finally, they may also flood the system with bogus entries. So as a consequence, log entries by themselves aren't trustworthy, at least not on a compromised system. And this is true for every operating system, every type of logging system. So regardless of whether I'm talking about Syslog, journald, or Windows Event Log, or even Apple logging system, once the system is completely compromised, meaning that the attacker has root or admin privileges, he can put in the log file whatever he wants. So we have to compare all this data with other independent sources. So there's one or two exceptions from this. First, when we have log entries being forwarded to another system, the entries stored there may be trustworthy, but only until the point in time where the system was compromised. Because from there on, the bogus entries by the attacker may also be forwarded, so we cannot trust them anymore. The other exception is when we can be sure that the log system or the root account was not compromised, so meaning that the adversary did not gain enough privileges to manipulate this logging system, we may have some confidence in the log also. So forensically, going through the three major log systems, first one is Syslog. We all know about this. It's the primary source of logging information on Unix. And it's been there since the BSD operating system line started. It's somewhere in the 80s. So, and a log message from a syslog point is just an unstructured ASCII text with a maximum length of 1024 characters. It's usually maintained, the log file, by a program called syslogd or rsyslogd or whatever, but it usually has something like syslogd in its name. And also, it's been along for quite some time. It hasn't been standardized. The first standard came out in 2001, RFC 3164, and it only described what was commonplace there. And they also did some work which took a few years to complete. And in 2009, the official syslog standard RFC 5424 came out, and which included quite a few more features and tried to standardize on that. When we also have logs on the system before syslogd starts, and this is on Linux kept in the kernel log buffer. And we can access this through def-k message or with the dmask command. And we also have a boot parameter to control that. But usually it just keeps the log messages in this buffer until syslog can empty the buffer and forward it to a file or to a log host. On the network, syslog is usually forwarded through UDP. On port 514 UDP. And being UDP, it's unreliable, messages may be lost. With RFC 3195, we have introduced TCP as a syslog transport, which introduces some reliability against message loss. However, not every TCP syslogd adheres to RFC 3195, so be careful when you chain different syslogd implementations together. And there are also some newer RFCs which add TLS or DTLS for transport security. So we have some confidentiality and integrity protection, but only on the wire. So collecting log files from Syslog is easy. We just go to the directory that's containing the logs, in this case, var log or var ADM log, usually, and copy the files here. And this may be changed in your Syslog configuration file, so you may have to look there to see where other log files are kept if you can't find them in the usual place. Some very old Unixes might keep them under var ADM directly, so it depends a bit on your implementation. If you have a central log host, we will have, of course, lots and lots of data there. And so we need to limit. So we need to limit in the time frame, usually something around the compromise, but not too much time before. We have to limit down to the affected hosts or applications, etc. The scope of the forensic investigation you have determined in advance will give you some points to adhere here to. And of course, from a legal standpoint, we have to observe things like data or privacy protection, even if we have a good cause to investigate logs, but we can't be too overly broad here because that would put us again in conflict with the law here. I'm not speaking about parsing syslogs, but when you've done this on your own, you know this is a tricky part because there are lots of subtle differences, especially in the area of parsing timestamps or IP addresses and host names and stuff like this. So even slight changes in the programming may tip your log parser off balance. So when we do the examination of log files and put this through some automated analysis, we should check very carefully that our log parsing tool gets what it's looking for, especially if we see that it's just returning nothing. As I've said, syslog files are just clear text files. So besides manipulating them, they can also read these log files when they are root or the log account and see what's being logged about their activities and can change their behavior accordingly. This is also true for clear text network traffic, so they know what is being logged about them. And of course, we can, as adversaries, modify the clear text log files. I've talked about this. One point about syslog is that we also may introduce false log messages without being root. So we can just pretend to be any application on the system and have our log messages logged as such. This is a bit of a problem when dealing with syslogd. So there are lots of other problems, especially with the unstructured log files. So people came up with a different solution. And I know this is being now a bit of a red cape for somebody. So let's talk about systemd journald, which is meant to be a replacement for syslog on Windows system and Linux system. So let me share a different screen here. Is it the right one? Yeah. No, it's not. Oh, it is. So. Ist das nicht der richtige? Na, egal. Let me just make it a bit bigger here. Doesn't this work? Okay, I think it's now to be seen better. So systemd journald is a part of the systemd suite of tools, and if we think of it, it's being used on my system. You can see there's quite a few pieces of systemd journald, and the one system part we are interested here is the systemd journald service. And we can see it here when it's being started on our system. It also has quite a few other sockets where it's listening on, but for now, just see if it's running here. We can check this with system control. And if we want to see a message from the journald, we can just put in journal control, just see one message here as a simple text message. This is not too much different from examining just an ASCII file. In fact, journal control is just reading the files and piping the output to less on your Linux system. You can also go to the end of the log file here. And but one thing about this is that we also have a more structured log format, and we can see this when you put in the output format of being verbose. And as we can see, it stores some data points here, like the systemd sessions. The machine ID is somewhat interesting because it's this long UUID type like string, but it also has stuff like a priority because this message came through Syslog. It has the real message text, but we can also see something like group IDs or the command or the exe or the command line that was being used. We can also use different sorts of output like JSON, which is mostly the same, just formatted as JSON. So it's probably not that much interesting. And the configuration of the log file is kept along with the other systemd configurations in etc systemd, and usually they are under journald.conf. So that's just an ASCII file that we can modify. And for here, let me just introduce two parts. One of them is storage, and one of them is a seal parameter. Storage means where does journald keep its log files? And as you can see here, it's set to auto, and that means where journald keeps its log file is dependent on which directories exist. If it's kept to volatile, stuff is usually kept under run log journal, which is not present here. And the other cases, persistent log files are kept under var log journal. And as you can see here, this is the machine ID, which is kept here in a subdirectory. And when we see one step further into it, we see a bunch of files with a very cryptic and very long file name. Systemd keeps its log files in different locations. Usually it's one for the system itself and one per each user ID that's logging on the system. So we have one here for nobody and one for the user with the ID 1000, which is just me. And the extension here, as you can see, is composed of 3 blocks. First of one is a general ID of the log file. The other one is the first sequence number of messages that's in the journal. And the last one is a timestamp in hexadecimal. So when we go into bar log journal and our machine ID, we can also put in journal control minus header minus file and see what's in there. And it gives us all the stuff here. We have a sequential number ID, which is here is the sequential number, which is the first record in here. Now where it is, 36,000 should be here somewhere. Okay, just blind today. Oh, forget it. So, and the other part is the timestamp. So if we just put this to date, we make it the ASCII representation of it. And divide this by 1 million. And so it should be January 10th, where the log starts, and yeah, add real-time timestamp. Okay, that's when the file was being logged. Okay, let's move on here. So as we can see, system control log files can just be copied, but they are in fact binary files. So when we see a bit in here in the system control log file, we see that's just binary data. So we cannot read it directly. We have always to examine this with journal control. And but we can copy the files just like we do with Syslog. And one feature that we have in system control is some sort of sealing. So we can cryptographically sign blocks of messages. And this is done here through a sealing key, which is generated with journal control setup keys. It's called the FSS, the file sealing key. And it also generates a verification key. So when you come along a system system running journal D, and you see that it's running with this FSS data file, and you also see that in systemd journal D conf, the seal yes is set. You may have the opportunity to verify the journal for its integrity. This is done with the command verify, with the option to verify. So, and when we do this here, we'll usually just stop. So, and it usually means when we do this without the verification key, we will not have a past verification. So let me put this in here. So as we can see here, it still failed its verification, but we get a message here telling us where the file corruption started to fail. So let's see if we can have another journal that is probably not corrupted. This may also happen if you don't shut down the machine cleanly. So then the last blocks will usually not be cleanly verified. Let's try this one here. So we can see here it's passed. One caveat here to mention is that we need to be careful with the verification part. If it's not sealing enabled, the verify option will just check the file for general signs of corruption, and we will still say that the verification has passed. So we need to be a bit careful here. So that's all I have for systemd. Let's go back to the slides. And here it is. So we also have the audit logs, which are kept under var log audit, but just another system where we keep logs, but usually only kept on the same system. And we can collect this like any other file. Antiforensics is probably a bit more complicated because if something like mandatory access control has been enabled, then these logs might be secure, but usually this is not the case. So the other part we have is the Windows event log. This is a logging framework put in by Microsoft for the Windows NT family of operating systems. It's a binary format, and until Windows XP and Windows Server 2003, this has the .evt extension. And since Windows Vista, we have an XML-based format, which is kept under the file extension of evtx. And these events are collected under Vista and up to Windows 10 and following by the Windows Event Collector service and then written to disk. Again, if we want some message text from the event log, we have to go to the message catalogs. Because logs under Windows and journal control as well are kept in, it can be internationalized, and these message texts and templates are kept as catalogs on Journally and as dynamic link library files on Windows systems. So the forensics for the old style event log, if you still have some XP or 2003 servers around, they are usually kept in system root system32 config, and the exact location is kept here under this registry key, services event logs. And as long as this system is running, we cannot copy these files because they are locked by the system account. So we can copy them only if this is done offline. Or we have to export the logs we are interested in through some event log command. So, and if we want to parse the log files, you should also go to the DLLs and copy them also. Because applications may add their own message catalogs, and if we don't have the message catalogs, we will just end up with a binary file with some pieces of data in where you can't tell what it's being used for. Same goes basically for the event-x format. It's kept in a bit different directory. Here it's a WinEVT logs, and it's a lot more log files here. It used to be some half a dozen log files until Windows XP. Now it's something like 50 or so. And again, the exact location is kept in the registry, and here we can copy these files if we have admin privileges. Or we can export them with filtering on the command line through the evt util command. And again, we have to look into the DLL locations for the Windows XP files. So I think that's it from my part for the log files. Before I hand over to Toby, let me check if there's some questions in the chat. And Syslog with reliability event logging protocol, RELP. Yes, of course, you can forward Syslog through any other protocol that you may see suitable. It depends on your local installation and what your Syslog implementation supports. You can also forward locally your Syslog to journal control and have that forward its journals. This is done through an HTTP API. Again, this depends on your tastes, how you forward your log files. There are by now lots and lots of other ways to forward log files over the network. I did not cover them all here. That would be a whole webinar on its own. So I think that's all the questions here. I see nothing in the Q&A, so let me hand over to Toby.
Excellent, thank you. Let me try. Hopefully you can hear me already.
Yes.
Let me try. Excellent, thanks. Let me try to share my screen, and hopefully you can now see my slides.
Looks
my title
good.
slide, anyways. So for the next, I don't know, half an hour-ish, let's talk about collecting network traffic. Now, the first question obviously is why would we want to do that? Because it has a number of real great advantages over the evidence we have seen so far. Usually, the network traffic itself cannot really be manipulated by any attackers, meaning that, as we will see in a bit, for instance, Netflow data is generated by network equipment along the way, which is hopefully, at least, doesn't have to be, but doesn't have to be true, but hopefully not under control of the attacker. The network traffic itself cannot be made to disappear, as an attacker might be able to pull off with, say, a rootkit on an owned machine. But the network traffic itself, if the attacker needs to talk to some other instance on the outside, then there will be network traffic. There cannot be no network traffic if communication actually takes place. However, having said that, of course, there is a way that the attackers try to counter this, and that is camouflaging, which is hiding in plain sight, essentially. So you might, as an attacker, consider, if I need to talk to some other instance somewhere on the internet, then I would maybe like to hide within a large amount of data that is going out to legitimate services. And of course, which would make it very hard to find the needle in the haystack, so to speak, of the actual malicious, or let's say interesting content that I'm trying to find. So the network traffic is still there, but it's not as easy to find. Also, obviously, one thing that an attacker can do is to use encryption. Depending on how well this is performed, it's next to impossible to actually get back to the data, as we all know. However, even if the payload is encrypted, then the actual communication, the fact that communication exists and the communication metadata is still there and must be in plain text, otherwise it couldn't be routed. So even if the content is encrypted, then the relationships, the communication relations, are still apparent and can be analyzed, which is a huge advantage. So in principle, the network-based evidence is really hard to fake for the attacker, which makes it in turn attractive and valuable analysis. Of course, where there's light, there's shadow. So network evidence also does have its downsides. One of the major ones is, well, you get to see a lot of network traffic these days. If you look at the right places, then you'll be seeing, I don't know, within DFN we have 100 gig lines these days, not a problem. So that's a lot of data per second that you can potentially see, which means that if you need to analyze all that data, you will have a lot of work on your hand. You'll see many bits on the wire if you look in the wrong place with the wrong strategy. And also in many places, looking at network at communication in general. So in particular, looking at network traffic is a real quick way to get yourself in jail, or at least in legal peril. Let's phrase it like that. There's mostly it's at least frowned upon. So people are not happy if they find out that this is being done, if not even explicitly illegal, depending on where you are. So that's something you should keep in mind. So having said that, where would we want to look for network evidence? Let's say, for the sake of this talk, that that we know, or that we would like to see what this guy here does on the network. So this is just an example of a very simplified, obviously, very simplified network of your, I don't know, your university, you name it, your office, where you have your clients, which are connected, in this case, just through access points, which are in turn connected to, let's say, core routers, which are then connected through the edge router, through a firewall, to the internet, to the general internet. So and there's a number of places here that you can look and try to collect network-based evidence. Obviously, if you know that you are interested in this machine, then you can try to collect data on this machine, if that's at all technically possible. But then any component that I've colored in blue here, from the access point to the backbone router, to the edge router, to the firewall, any component here that is on the way between the communication of this guy and presumably some other endpoint on the internet, can be, in principle, intercepted and collected at these blue points. In addition, and this is why this guy here is also blue, in addition, you might have some interesting communication relationships with internal services. We'll see that just as an example. Let's say this is a DNS server. This might, if you have a look at this internet, at this network traffic that arrives here at this guy, then you might be able to see interesting stuff, even about the machine you're interested in, by correlating queries and stuff. So that's why this one is blue as well. So depending, obviously, on where exactly you're looking at, there's different things that you really can look at and cannot look at, and where it makes sense to look for different things. So in principle, there's two things that we can consider grabbing, right? One is get the entire network traffic, all the bits that are coming through the wire. Just store those things, write them out in what's called packet capture files. The format is usually PCAP or PCAP next generation, PCAP NG. That's just basically really just packets as they fly through the Ethernet or whatever network it is that you're using at that point. It doesn't have to be Ethernet. And stores that writes that to disk. This means that it contains everything that there is to be seen. This is kind of like in the persistent storage acquisition series. This is kind of like getting as close to the device as you can get, in that this contains everything, all the information there potentially is to be found at this particular place. However, as I've mentioned before, this is well, a lot, right? So this might be a problem in storing. So you can do this, for instance, when you're close to a particular device. Then that might be easy because we're talking maybe about a gig E, so a gigabit per second transport line. So line speed might not be a problem. You might be able to write that out. But if we're talking back-end routers, then you're very likely going to have a hard time sampling everything out. On the other hand, there's the concept of flow capturing, which is just grabbing communication metadata, not the actual content of the communication, but just the information that person A talks to person B, or server A talks to server B. The format that is used for that is mostly these days either Netflow or SFlow. We'll be talking about that briefly in a minute. The storage is not standardized though. So it's standardized how to capture it on the wire, but it's not standardized how you write it out, which turns out to be possibly a problem, but it's something to be aware of. So capturing packets. This is, as we just said, as we just saw, a record of the entire communication, right? Which means it's a lot, and which means it's also very likely to be, as I've already mentioned, very likely to be at least interesting in legal terms. Again, we cannot say this enough. We're talking very, very thin ice here. Privacy laws with the GDPR are well, you want to be thinking about that. The capture files can get pretty large pretty quickly. So again, same as for the persistent storage acquisition, you want to make sure if you start doing something like that, that you have an adequately sized backend to actually store that, and that you need the bandwidth to actually write it out somewhere. On the other hand, the more stuff you capture does not necessarily mean that you actually get more interesting evidence in terms of interesting for your ultimate goal. I mean, you're looking for evidence for a particular thing, for a particular, well, let's say crime or whatever. So more data does not necessarily mean you have more stuff that will help you actually prove something or show something or find out something. But it'll certainly it'll certainly mean that you have more data to go through. So it's always good to step back here and reflect and consider whether this is what you actually need in terms of filtering. And the closer to the source you can filter, the less you have to, the less traffic you have to analyze, and the less throughput you have to go through, and you have to provide. And it's also always a good thing to consider whether there might be other ways to get the same evidence, or to reach the same goal in terms of investigation. Is there anything that's less intrusive? Maybe not. Is there anything that's legally less risky? Possibly. But that's something to bear in mind. Having said that, how to capture packets at endpoints? Well, you can either capture traffic at the endpoint, at the device you're interested in, so at the orange guy in the picture, or on the other side of the communication, if that's at all possible, if that's within your jurisdiction or your realm, so to speak. For instance, if some bad guy, if some interesting compromised machine does a DNS query, and the DNS resolver happens to be on your premises as well, then you might, one feasible way of getting interesting information is to look not at the bad guy, but at the DNS resolver and see what queries it gets. So then, and this is actually something that works real well. So then if you see any queries for well-known fake domain, or well, fake fast flux domains that are indicative of malware infestation, then you know that whoever ran that query probably has some sort of malware on the system, and you can pretty much tell by the format of and the actual domain name that's queried which malware system is on that machine. How would you do that? How would you capture traffic? Well, at first and foremost, the primary tool to do that is interactively, anyways, is Wireshark, or if you're less inclined to use the mouse, T-Shark as a terminal version of this, or less interactively and more stuff to run in the background, you can use TCP-dump or NTOP, network top. It's another interesting project that'll do that. And of course, in the case of, for instance, the DNS server, the example that I gave, there's specialized software that'll just dump out the interesting packets. In fact, in this particular case, it's an edge case. You might argue that this is just logging that you're really interested in, but in principle, you get the drift. What you also can do is you can try to capture packets along the way from its origin to the destination. Where to do that at? Well, you can do it at hubs, if anybody still has hubs actually in use. At switches, at routers, and for those devices, you'll usually need to configure mirror ports or span ports, meaning that usually these devices work by offloading or by reducing their workload by only forwarding in traffic to the ports that they actually know that the traffic belongs to. And if you want to capture all the traffic, then, well, you need an extra line. And that extra line needs to get all the traffic you're interested in, so you can write it out into a file or whatever. To do that, you need to set up what's called a mirror port, which means it mirrors all the traffic. It gets mirrored all the traffic that's coming through another port, say. You can also, some network equipment, some pieces of network gear can also store the packet data, the PCAP data, or the packet captures themselves for a usually very limited amount. And so I don't think it's really useful in this context, but in principle, you can tell the switches, or there are switches and routers out there that will allow you to store packet captures on the devices. And you can also, of course, break some connection and introduce a sniffing device in that connection inline, which eliminates the need for something like a mirror port to exist. But of course, it means that you actually break the communication line, which in turn means that if your listening device fails, essentially it'll have to listen on one end and put it out on the other end again. If that fails, then your network connectivity is going down. So there's trade-offs here. IPSs sometimes work like that. There's interesting things that they try to do to have explicit hardware that'll allow the traffic to move through even if the sniffing device fails. That's an interesting problem in itself. So how to do that? In principle, you can obviously do any of the above. If you manage to run a TCP dump on your Cisco router, then you can do that. But there's specialized software that's made just for sniffing and analyzing and logging and alerting and getting through all that traffic. And the three most well-known projects here are Zeek, formerly known as Bro, Snort, and Suricata. And those packages will just essentially pull in all the packet data they can get, analyze them, store them on the fly, pull out alerts, all that kind of stuff that you would imagine. It's usually, well, it's fairly complicated. It's certainly worth a shot if you're interested in that, but it doesn't come for free. It does require some hardware that's potent enough to go through all the traffic, and it does come also at a cost in terms of resources and manpower, and in terms of, you know, you need to actually actively manage those things in order to be useful. So those are essentially the ways that you can get to full traffic or packet captures. The other way we can look at network evidence is Netflows or flows. What exactly is a flow? A flow is a sequence of IP packets within a certain time frame that share some properties. For instance, they all go from host A to host B, from port A to port B on that given protocol. So they're all in layman's terms, they're all the packets that belong to a given flow of communication. So say to an SSH connection, to a given SSH connection. Each flow carries a number of interesting bits and bytes of information, such as how long the flow took, as in it started at 10 a.m. and it kept going until 11 a.m. It had that many, so and so many packets containing so and so many bytes, that kind of stuff. It does not contain any packet payload, so no actual data that was transmitted. So it's somewhat more storage friendly in terms of this is a vastly reduced, usually a vastly reduced amount of storage that is needed, and it's somewhat more friendly towards privacy. So there's arguably it's better in terms of you don't want to get on people's don't want to tickle people's nerves. Storage is easier here, but it's still a real issue. These things even flows are not for free. On my home system, the flows of half a year take about on the order of 5 gigabytes of data. That's just one household, one router. For a larger university, let's say 30,000-40,000 users, I have seen in the past flow data in the order of a terabyte or two for a week. So that can add up. Also bear in mind that you're probably legally not allowed to store that indefinitely with the GDPR. So that's something to consider. Flows come in a number of formats that you might see. The most prevalent one in my experience is Netflow, which is defined by Cisco. In practice, versions 5 and 9, there's, I believe, I'm not sure how many versions there are, more than 9, I believe. In practice, versions 5 and 9 are relevant. Version 9 is the first that's standardized, described in RFC 3954. And it has been then worked into, based on that, the Internet Protocol for Information Export, IPFix, was actually standardized. It was based on Network Protocol, Netflow version 9, but it's the spin-off. And that is standardized in RFC 7011 and 7012. And you can, usually in many devices, you can switch the output format between Netflow 5, Netflow 9, and IPFix. That's at least many times the options that you'll see. Then there's S-flows that you're likely to encounter, which is defined in RFC 3176, run by sflow.org. This does not produce Netflow data, just samples of flows, right? So it just writes out every, say, 200th packet and tries to assemble some statistics. This is fairly useful for network analysis for networking guys, as in scaling, detecting mismatches of resources, that kind of stuff, congestion detection. But it's for forensics, in my opinion, it's less useful because at least in my experience, since it samples, the flows that you're actually interested in never kind of show up. It just kind of turns out that the flows you're actually interested in never in there. So there's of course other standards that are used by other vendors, too numerous to list them all. Just as a few examples: JFlow by Juniper, NetStream by I forget who, CFlow-D by I forget who, Nokia I think, RFlow-D, AppFlow, TrafficFlow, Microtik, a number of formats for capturing these things. They're all more or less the same. Sometimes compatible. Sometimes you can just use them, those formats. Sometimes you can't. Depends really on the setup, the tooling, how you need to work with that. And finally, there's remote network monitoring, MIB. For this is an SNMP playbook. This is more geared towards, again, analysis of network health, so to speak. Not so much for forensics, but just as a to keep it complete here. So how to capture flows? Usually you collect them of course over the network. If possible, you can export the flow data directly from a given, say, router to your investigator's collecting machine. It's usually called a collector. If you can do that, and you might see the situation where that you cannot have a router export flow data to more than one collector device. In which case, if you need the data on more than one target device, on more than one collector, for instance, the networking department would like to see the NetFlow data for their own reasons, for their own purposes, for resource management, and you as a forensics guy would like to see, with your forensics hat on, would like to see NetFlow data for forensics reasons, and then you might need two separate collectors, and then you need to have a samplicator, for instance, that will just duplicate the data in between. What exactly is transmitted here, and it depends, of course, depends on the protocol and on the protocol version. So NetFlow 5, NetFlow 9 varies in the details in the fields. You'll have to be careful at what versions you use, so that you actually get the data you would like to get. And of course, you can collect that if the NetFlow data is already stored somewhere on persistent storage, then you can, even though it's not standardized, you can of course copy the data. Hopefully, you can then use the data to by whatever tool, with whatever tool you'll try to import it to. But in many cases, it's possible to re-export the flow data to another collector, in which case it is standardized again, because that bit is standardized. So some useful tools to collect and to analyze flows. The grandfather of all these flow collection and flow analysis tools is NFZen and the NFDump suite by Peter Haag. That's been there since the 90s. And there's new projects like CFlow-D, like Silk, like vFlow, IPFix by Collector 2 by Sysnet. And then there's tools that are sort of related, Argus and YAF. Argus and YAF will collect packet data, so full wire captures, and then in particular create NetFlow data out of that. So those are tools that you can keep in mind as well. So final slide. My 30 minutes are up anyways. So the final slide here. Also keep in mind that there's other networks that might yield interesting evidence. Just to name a few: DECT, mobile phone networks, Bluetooth, Zigbee, NFC, RFID, ERDA, the loopback interface even. There's plenty of stuff here around that might contain interesting data for your investigation. So keep in mind that there might be other sources. Just as a side note, Wireshark, the tool that I referenced in the beginning, will work happily with many of these protocols. It's amazing how many protocols Wireshark can interpret. So that's a really versatile tool. With that, thank you for your attention. Since Klaus started that tradition, I'll just continue with that and see if there's any questions that people may have right now for this part of the talk. Yeah, PCAP or didn't happen exactly. Oh, forgot to mention that. One thing you want to make sure is there's timestamps in the Netflow data and in the PCAP data that you store. So as always, when it comes to timestamps, you want to make sure that you actually know the time zone that the system who produced the timestamps actually is set to. Right? This is crucial. This is one of the things that constantly trip you over if you're not aware of it. Cannot stress this enough. And in Europe, we're in the unfortunate position that, well, it's not really obvious if something's off. If you're in Japan, then you're -10 or something. You have a 10-hour difference, so it's obvious fairly obvious if a timestamp is local or UTC, which are the two big suspects. But if you're in Europe, it's an hour or two. That's not really obvious. So keep that in mind. Cool. Going through the notes or through the chat right now. Is there? I don't see any questions. Excellent.
No, I don't think so. Thank you, Toby. Thank you, Klaus.
Excellent. Let me stop sharing my screen and hand back over to Klaus. Thanks.
Brilliant.
Yeah. Thanks a lot, Toby. And let's continue with the last part of this session. So it's a code collection of other data. As I said, this is data that does not really reside on the image's system and is not necessarily available in some sort of central databases or logs. So to get at that data, we might have to interview people to get this data. And when interviewing people, we know, especially when some sort of investigation is going on, we should be careful what we ask and how to ask this. In general, it's best to leave the questioning up to some people that are trained in this, like a law enforcement or an attorney. But if we are doing the investigation on our own, just be careful here, make them feel comfortable. It's not usually in some sort of trying to get people hanged, but they will be nervous, and so just don't be too nosy when asking question about what they did and what they use the system for or stuff like this. Besides that, if we have assigned names or addresses, these might be subject to change, so we may have to collect historical data. This can be done through some sort of passive DNS monitoring in public DNS databases. The WHOIS database is there, which gives you contact information for networks. It's not changing very often, but it may change. The internet routing databases may change, especially if somebody puts up a route to some subnet of yours. We may get some hints from there. Locally, I've spoken about this, the ARP tables or CAM tables, quite volatile here. This may also be in the logs, but especially if we are working with incidents, the mappings from DHCP or NAT are very important. And if this sounds familiar to you, yes, that's exactly what all the data preservation talks are about, with all their implications. And with all the attempts to push this up upon us on a broad scale. I'm not going into this here because it's taking a bit too far, but I have to admit that as investigators, this is very important and very useful information. So there is a point when law enforcement wants to get a hand on this data, because without it, they will not stand much of a chance in ever clearing up any cases. So the point is here, we have to collect the target state as defined by the policies, not so much what's on the system itself, but we will then correlate, meaning compare what it's on the system or on the hardware with what has been defined by policies and knowledge of people. So what we are talking about, first there's some sort of technical data that we still might need to have before continuing with the investigation, like where is the compromised system now? If it's a server, it's in some sort of building, in a room, in a rack, where it is. So if we have a large data center, this is something that might not be entirely obvious. And even if you have a small university outpost somewhere, it may be some broom closet with a rack in it. And so when we need that, system, or we want to copy that, we have to get to it. We need the keys to the building, or somebody has to let us in. So we need their phone number or something like that. This is, I call, surrounding data. Or if it's a laptop or a mobile system, we might need to know where it's stored now. It's still with the user. Where is he? Is he at home? Or has he handed over this to some guy, his superior, or is it kept in somewhere in the room? Is it in a closet? Is it closet locked? So we may need that data. Then there is the state of the hardware itself, especially if we try to deal with laptops and mobile devices, or even on servers. Are there some traces of physical manipulations or break-ins? So that may be the case that we see scratches on the casing or on the screws. Many of us will inadvertently scratch screws when we try to loosen them. Well, that's easy to spot on a new system. If we have something like a heavily used phone or laptop, yeah, we don't have to bother with scratches or other traces on the surface of a system, because it may be so scratched that we can't tell it. But another point that we have to watch for is the cabling. Where do all the connected cables lead to? We had cases where once a system was hidden in the ceiling tile, beneath the ceiling tiles of a data center. So we really had to follow the cabling from another system up to somewhere in the ceiling where we found that system. Or we see other cables that are laying around near the system, which are seemingly unconnected, but probably they were connected in the past. So then there's the peripherals that were attached, any diskettes still left in the drives, or SD cards or USB sticks still sticking on it. There may be other USB devices, think of keyloggers, video cameras, even complete embedded systems disguising as USB devices. There may even be other hardware that has been built into it, like somebody may have attached another hard drive inside the system, or attached additional cards or devices to internal bus interfaces that are on the main board. So when we do that kind of information, it's advisable to take pictures before and along the investigation. So then there is non-technical data, especially around users. First comes to mind the mappings of user IDs and usernames, which may be gotten from LDAP or Active Directory services or some identity managing system. You may have even a network information system or yellow pages if you have very old, historically grown Unix installations. But there are also things like the login patterns of users. So what are their typical work hours or shifts? So we can see if somebody's logging in at 3 o'clock in the night, it's probably not them. But on the other hand, especially with home office today, it may still be the case. So we might have to ask him, were you accessing your system? Were you working late at night? Maybe. Or he's been on holiday or sick leave, or maybe he was traveling and in a different time zone. That may explain the timestamps here. So we have to keep in mind that. If we have home users, especially, we might have to look at the IP address pool of their home ISP, so we can rule out logins from that pool of IP addresses as being most likely coming from that user itself. So, and if we see different IP address pools here logging into that user ID, we might be getting suspicious. Other things are usage patterns on the system, so like the type of programs used. So if we have a non-developer, somebody just doing office work, they will usually not use compilers, but an adversary compiling his toolkit may use this. So this is some sort of information we might find useful in filtering out what is suspicious and what not. Same goes for documents used. So anything outside the user's home directory or the typical directories he's working on might be raising our suspicions. So if he's accessing other home directories or things like on different drives, which he's not usually working with. There are patterns of network usage. So in all these cases, we may have to contact the users or his peers, like is this normal to visit some sort of websites here, remote logins, peak times, where are the top number of users or the amount of data transferred from a system. So we see lots of data being transferred from a server and it's not the time of the backup. This may raise some suspicion because it might be data that is exfiltrated. Then there is the role of the system itself. So if we know that's a database server or web server, it should probably not be running much other services besides that, at least not network-wise. So, and besides that, we may look into the configuration of these systems. So if we know it's a database server, we may also have a look into this, which databases and schemas it needs to rule out database rootkits or other databases that are kept beside this here. Is web content served from other unusual directories, which are not usually the case. So we need to look into the web-based directories, the web server modules that are used here, which are the ones needed and which are not, the content management system. With the case of DNS servers, we may look into the role as, is it an authoritative name server? Is it a caching name server? Is it forwarding? What zones does it serve? Etc., etc. The network configuration of the system, of course, is very useful. So if we see IP addresses that should not be used on that system, that may raise our suspicion, or if a system is being configured in a way that is not standard for that system. So if I have, for example, IP addresses that are usually handed out through DHCP, but I see an IPv6 address being handed out by stateless automatic auto configuration, Slack, this may raise my suspicion because somebody may have turned on Slack support on the router. Are there interfaces that should not belong there? Attackers try sometimes to establish tunnel interfaces or some virtual interface to work with. How does the local routing table look like? Is the default gateway probably be changed? What should the default gateway be? So we may have to ask the network administrator here. Same goes for the local resolver. Which name server should be used? Or what's in etc host, or what's supposed to be in etc host? This is especially important when attackers try to disable antivirus downloads by adding something like localhost mappings for some specific system. And then there's a case of network mounted drives. So all this is stuff we may have to ask people like network administrators or even the users themselves about. So that concludes this session. Let me just wrap up a bit more. As I've seen, there's more evidence than memory and disk images. So we should collect log information from central log hosts. We may have the need to do some packet captures or some IP flow information. And we also may have to collect some historical data and other data. This is the end of this series of webinars. And to improve and to continue with our series of webinars, we, of course, need your input and your feedback. So please fill out the surveys I ask you. And the survey will also probably include some way to give us some hints for the upcoming part of this, for the next series, because we've taken you now through the part of collecting evidence, but what we've not covered yet is how to analyze it. And this will be covered in the next part or the next series of webinars, where we'll cover analysis tasks in more detail, and we will cover some of the more common tools like autopsy and volatility. And if there are some tools or some questions you may like to have covered, please include this in the survey. And if it's about tools, please try to limit yourself to open source tools, because, well, we don't have the budget to acquire some commercial systems for evaluation. So, and also let me thank you for all your patience and all your support so far. And I hope to see you back soon in the next series. And I'm still open for praise, criticism, questions, and more.
Great, thank you, Klaus. Thank you, Toby. Really interesting sessions. Thank you so much for those. A lot to think about, particularly in terms of you know, accessing data running across public networks, and what people can see and what people can't see, and so on and so forth. It's really interesting areas. Just to say, I've put in the chat section a couple of links to the YouTube playlist where all these videos will be, and also to the forensics page, where all of the information will be available, PowerPoints and so forth and so on, will be available on the Learning website very shortly. So if you capture those URLs, you'll be able to find all the information later. Thank you. We have one question. Is there a mailing list to get information when the next training will be? I don't know. I'm going to be honest, Roland. What I will do is I hope that Irina will be able to circulate links to all of the various people who registered, because obviously we have your email addresses. Whether that will be a formal email mailing list or not very much depends on GDPR, as we all know and love it, because it may not necessarily be that you have permission to send you regular emails about new stuff, but we'll see what we can do there.
We try to announce the next series through the channels on TFC-CERT and the local networks also. So if you happen to see this, yeah, spread the word, and we will announce this soon when we will do the next series of webinars.
I would hope that our GDPR people would allow us to say, you attended the first series, you can probably want to attend the second series as a one-off, but we will have to check with those guys to make sure that we're allowed to use data. I mean, obviously having a data extraction and forensics course, which would then breaks a lot of rules, is probably not a good idea, but we'll see what we can do in that respect. Okay.
I'll probably just do one more screen sharing here, because everybody is now putting in slides, links about USB devices. I've forgotten this. This is a famous rubber ducky, which just acts like a keyboard, and where you can enter some predefined keystrokes. There's a USB keylogger, which is very small, just a small pack. But there's a voice recorder or a spy cam also that we can have. These are just a few examples I've grabbed from the network yesterday. So just one more year.
Absolutely. It's a dangerous world out there. Thank you very much.
Yeah.
Thank
so
you,
be
Klaus.
careful what's attached to your systems.
As always, and of course, bring your own device is a huge issue with our community, because we have no idea what any of the students are bringing in, because that's, you know, part of their nature. They are buying their own laptops, they're buying their own Macs, they're buying their own whatevers. We have very little control of what they're connecting to our networks, which is always a potential risk.
Okay.
Okay, thank you so much.